GenAI and MLOps Part 18. This episode has 8 questions. For each question, take a moment to think through your own answer before I share a strong approach. Question 1. What is concept drift? Here's a strong way to approach it. Concept drift occurs when the relationship between input data and the target output changes over time, causing the machine learning model's predictions to become less accurate. In simple terms, the model may still receive similar data, but the meaning or behavior behind that data changes. Example: in a fraud detection system, fraud patterns and attacker behavior may evolve over time. A model trained on old fraud patterns may fail to detect new types of fraud. Concept drift is important because the model logic itself becomes outdated even if the input data format remains the same. In MLOps, concept drift is handled through continuous monitoring, performance tracking, drift detection techniques, and periodic model retraining. Nice. Let's continue. Question 2. How do you detect drift in production? Here's a strong way to approach it. In production, drift is detected by continuously monitoring both input data distributions and model performance metrics over time. For data drift, we compare production data with training data using statistical methods such as PSI, Population Stability Index, KL divergence, Kolmogorov-Smirnov test distribution comparison, and feature statistics. We monitor features like mean, variance, null values, category distribution, and data patterns. For concept drift, we monitor model performance metrics such as accuracy, precision, or recall, F1 score, prediction, confidence, error rates. If these metrics degrade significantly compared to baseline performance, it may indicate concept drift. In production environments, we usually implement automated monitoring pipelines using tools like Prometheus, Grafana, MLflow. Evidently, AI labs. Once drift crosses a threshold, alerts are triggered, and automated retraining or rollback workflows can be initiated through MLOps pipelines. Great. Moving on. Question 3. What tools are used for drift monitoring? Here's a strong way to approach it. Common tools used for drift monitoring in MLOps are Evidently AI, used for data drift, concept drift, data quality, and ML monitoring dashboards. Y Labs, Enterprise ML observability platform for monitoring drift, anomalies, and model performance. MLflow, used for experiment tracking, model versioning, and integrating monitoring workflows. Prometheus plus Grafana, commonly used for infrastructure, latency, custom ML metrics, and alert monitoring. Amazon SageMaker Model Monitor, Oz native service for monitoring data quality and model drift. Google Cloud Vertex AI model monitoring, GCP service for monitoring skew, drift, and prediction quality. Arize AI, advanced ML observability platform for production model monitoring and root cause analysis. Fiddler AI, used for explainability, fairness, drift detection, and model performance monitoring. In real production environments, teams often combine ML-specific monitoring tools with traditional observability stacks like Prometheus, Grafana, Elasticsearch, and cloud-native monitoring services. Alright, next question. Question 4. Explain model versioning. Here's a strong way to approach it. Model versioning is the process of tracking and managing different versions of machine learning models throughout their life cycle. It helps maintain reproducibility, traceability, and governance by storing details such as model artifacts, training datasets, hyperparameters, code versions, performance metrics, environment configurations. In production, model versioning is important because multiple versions of a model may exist for experimentation, testing, rollback, or retraining purposes. For example, if a newly deployed model performs poorly in production, we can quickly roll back to a previous stable version. Model versioning also helps teams compare model performance, track changes, and ensure compliance and auditability in enterprise environments. Common tools used for model versioning include MLflow, DVC, Kubeflow, weights and biases. Amazon SageMaker Model Registry. Typically, versioning is integrated with CI or CD pipelines and model registries as part of an MLOps workflow. Let's keep going. Question 5. What is experiment tracking? Here's a strong way to approach it. Experiment tracking is the process of recording and managing machine learning experiments to track how different models perform under various configurations. It helps store and compare details such as Training datasets, hyperparameters, model versions, source code versions, evaluation metrics, training environment details. The main goal of experiment tracking is reproducibility and comparison, so teams can identify which experiment produced the best performing model. In production ML environments, multiple experiments are usually performed with different algorithms, parameters, or feature sets. Without experiment tracking, it becomes difficult to reproduce results or understand why a particular model performed better. Common tools used for experiment tracking include MLflow, weights and biases, Neptune AI. Kubeflow. Experiment tracking is a key part of MLOps because it improves collaboration, reproducibility, governance, and model lifecycle management. On to the next one. Question 6. Explain ML reproducibility. Here's a strong way to approach it. ML reproducibility means the ability to consistently reproduce the same machine learning results using the same data, code, configuration, and environment. In simple terms, if another engineer runs the same ML pipeline with the same inputs, they should get the same model performance and outputs. Reproducibility is important in production because ML systems involve multiple changing components such as training data, feature engineering, logic, hyperparameters, model versions, library dependencies, infrastructure environments. Without reproducibility, debugging, auditing, retraining, and rollback become very difficult. In MLOps, reproducibility is achieved using version control for code and datasets, model versioning, experiment tracking, containerization using Docker infrastructure as code, CI or CD automation, dependency management. Common tools used for reproducibility include MLflow, DVC, Kubeflow. Git. Reproducibility is one of the core principles of reliable and production-ready MLOps systems. Good. Here's another one. Question 7. What is feature engineering? Here's a strong way to approach it. Feature engineering is the process of selecting, transforming, and creating meaningful input variables, called features, from raw data to improve machine learning model performance. The goal is to make the data more useful and understandable for the ML algorithm so the model can learn patterns more effectively. Common feature engineering techniques include handling missing values and coding categorical variables, normalization and scaling, feature extraction, feature selection, creating derived features, date and time transformations. Example: from a timestamp field, we can create features like day of week, month, weekend, indicator, peak hour. Flag. In production ML systems, feature engineering is very important because model accuracy often depends more on data quality and features than on the algorithm itself. In MLOps, feature engineering pipelines are usually automated and version controlled to maintain consistency between training and production environments. Nice. Let's continue. Question 8. What is feature store? Here's a strong way to approach it. A feature store is a centralized system used to store, manage, version, and serve machine learning features for both training and production environments. It helps ensure consistency between the features used during model training and the features used during real-time inference. A feature store typically provides centralized feature management, feature reuse across teams, online and offline feature serving, feature versioning, data consistency and governance, low latency access for real-time predictions. In production ML systems, feature stores solve common problems such as duplicate feature engineering efforts, training, serving, skew, inconsistent feature calculations, difficulty managing large-scale feature pipelines. Example: customer-related features like purchase history, login frequency, or average transaction amount can be stored once and reused across multiple ML models. Popular feature store tools include Feast, Tecton, Hopsworks, Databricks. Feature store in MLOps. Feature stores are important for scalability, reproducibility, and maintaining reliable ML pipelines in production. Great. Moving on. That wraps up this episode. Nice work practicing, and see you in the next one.